And I'm going to now hand this over to Raleigh, who is going to
convene
this panel.
All right. I'm Raleigh Hood. I'm from the University of Maryland Center for Environmental Science, and I'm going to convene this panel. And so first, Margie already mentioned who our panelists are, but I'd like to start by giving our two panelists who didn't give talks this morning, Reynard Najar from Penn State and Gulvin Laurel from the Free University in Brussels, correct? And so just give these two guys a couple of minutes to say a few words about what they do, their interests, and then I think we have compiled some questions that we can put to the panelists, but I think maybe we'll just hand it over to the audience first, and then if we need to interject some additional questions, we'll do that. But let's start with Ray, perhaps introducing himself.
Hi, everyone. Is this on? Maybe? Yep. Can I get a little bit of a response? Yes. All right. Great audience. Yeah. I'm Ray Najar from Penn State University. I work on, in recent years, mostly coastal biogeochemistry and carbon cycle and some climate change issues. And the carbon work I've done has been a lot of it has been quite synthetic. I guess recently we had a paper about budget for carbon budget for the East Coast of the United States, from the head of tide all the way out to the continental shelf. I also contributed to the soccer report that you heard Heather talk about earlier that had 4 aquatic chapters in it, and I was the one of 5 science leads for that report, and I helped coordinate those aquatic chapters. And I think I'll have a slide here. We don't have to clear it up now, but
it's up.
It's up there. Okay, yeah. So this is sort of a very broad brush kind of outcome of the soccer, at least the aquatic portion of the soccer report, which tied together those 4 aquatic chapters. And I think we have at least one of the co-authors here. Wei Chun Kai was a co-author on the Tidal Wetlands and Estuaries chapter with Lisa Marie Wyndham-Myers. And this was an assessment, and we simply tried to take all of the information that we had at hand. A lot of it is quite sparse, as you can tell from some of the error bars here. I think wherever you see 2 stars, that's we're plus or minus 100%. So you can see that a big part of this activity was to really identify what were the what we know and what we don't know. So as you can see, there's a lot of work to do. What else can I say? That's probably enough for now. Yeah.
And Gulvin.
So my name is Gulvin Laurel. I'm coming from Belgium, so the Université Libre de Bruxelles. So that's the French-speaking Free University of Brussels. Not to be confused with the French University of Brussels, but Flemish-speaking. You have all the details. But I'm French-speaking at the accent quality over there. So I'm working a lot on CO2 fluxes at the air-water interface, mostly in estuaries and continental shelf waters. And so I have been working at different spatial scales. So I've been working on an estuary model, which has been applied to individual systems, or at the regional scale, to several systems in a row. And also I've been developing continuous PCO2 maps for the continental shelf sea. So along the east coast of the US, also with Wayne June, I have worked on trying to come up with a budget of estuarine outgassing from all the Atlantic coast. And also a little bit earlier, we tried to make a sort of integrated budget taking into account rivers, estuaries, and continental shelf. So I'm very interested in this upscaling and for regional and global budget techniques.
All right, thank you, Ray and Goldman. So yeah, let's just go ahead and turn it over to the audience to ask questions to all of our panelists or specific panelists about their talks or what was just said. Any questions or comments? Susanna?
Thank you. One topic that was not mentioned, but is related to the CO2 balance and increased CO2 loading, increased carbon loading, increased respiration, increased net heterotrophy in the river mouths, is ocean acidification in the eastern seaboard, which is not something that we naturally relate to that environment, but I think it has been reported, right? So I would like the panelists to comment on that.
Any takers? Come on.
He might be the guy right there to do it.
I'll just say that there's a really nice poster by Wageman student 1-1 showing acidification off the continental shelf, a very strong slope downward from 1960 to the present time. So that's probably more up to date than I could show.
Well, what's interesting as well is that we can follow what's happening in...
Is that mic not?
What?
Make sure it's
Sorry, is it okay like that? No, okay, well, then I'm just going to speak loud. That's okay. Thank you. Thank you. Oh, yeah. Well, oh, yeah. I see the difference. So, yeah, what did I say? Yeah, oh, yeah. So, the continental shelves, obviously, we can follow the ocean acidification there, but that also sort of propagates upstream into the estuaries. So, also still with Wayne June, we looked at simulations with estuarine models to try to see how much time it takes for the disturbance, the perturbation at the marine mouth to be felt upstream in the estuary with some event of ocean acidification, and what type of geometry or behavior of the estuarine system might enhance this perturbation or sort of protect the system from it. So.
There's one thing I'll just add about ocean acidification that maybe hasn't gotten a whole lot of attention. It's something we've been thinking about a little bit in a paper we're working on for the Chesapeake, is the changing alkalinity load to coastal waters and what effect that might be happening, and also what other processes in estuaries that might be occurring sort of independent of other things. And something that hasn't been thought about a whole lot is the impact of invasive species on carbon cycling and on acidification on an alkalinity budget. Something we're finding, perhaps not definitively, but there's a very strong suggestion that that an invasive clam in the Potomac River has had a big impact on the alkalinity budget there. So there are other, with regard to ocean acidification, there are other things that are happening that, I mean, honestly, I hadn't thought about until the last AGU meeting when I spoke to Laura Harris about it, and she suggested I look into this as an explanation for a big alkalinity sink that we had found in the Potomac. So there are these other aspects of carbon cycling that perhaps we hadn't thought of that could be quite important.
So I just might mention in Virginia, at least, there's been a huge increase in aquaculture. And so when you culture, for example, clams, there's a huge amount of sulfate reduction, which we're not clear, it's not clear yet how that will affect alkalinity in the region. But I think eventually it has to, because it's such a big, taking such a big area.
Okay, any other comments on that? No, well, we have a question from Wei Jun here, but Patty, okay.
Hi there, Patty Matrai. I want to come back to a comment that Iris made on extreme events, and that is we've had in the Gulf of Maine, some of the wettest years in the last 100 years. And that's not, hence, increased river flow, but also precipitation. And so how do we go forth with that when perhaps we don't quite have the mechanisms to record those effects and quantifying these sort of stochastic rather than regular samplings? Thanks.
What's your area?
She mentioned you. I think that means you have to answer the question.
Those guys are the modelers.
So are you talking about precipitation directly on the water surface? Or, I mean, you said precipitation in contrast to runoff, I thought. And so,
Both of them are part of these wettest years, but the wettest years is the issue of precipitation, both snow and rain.
So it's not just what they're introducing. So riverine inputs, I mean, it can introduce all kinds of things like alkalinity as well as, but it's also affecting freshwater flushing time, and that has a big effect on net ecosystem metabolism and the fate of carbon. So long residence time, we saw in lots of talks, it had a big effect on nitrogen retention. And so the question is, how do you model that?
I don't know.
All right, we have several hands have come up. Wei Jun, do you still have?
Wei Jun, University, Delaware. I probably shouldn't ask, but three of this side are my co-authors in synthesis, and I talk to you a lot, and you. But anyway, it's a very wonderful session. Started with Anthropocene carbon cycling to the nutrient one. So my question is this. We know from pre-industrial to today, there are a lot of changes. One hypothesis is during pre-industrial time, the coastal ocean estuarine must be a CO2 source because we decompose organic matter that's synthesized in the land. And now because of the nutrient input, eutrophication, and other reasons, climate change, so the coastal ocean become a CO2 sink. And so I see, to me, each of you could have gave your perspective on that, and I think it would be interesting to the audience too. So this carbon sink to source, yeah. Source to sink.
I can speak from my work because I don't do carbon, but I've just reviewed a paper, hopefully coming up soon.
Your nutrient input is very relevant.
Right, so they also have nutrient input. They are trying to, they did 5,000 year simulations, MPI work. And then they still suggest that coastal oceans are a big source right now on global scale. But
yeah, depending on how big should we include the estuarine or just the continental shelf.
Right.
It's just a sink like now.
Right.
So but the relative change from the nutrient input, when you have more nutrient input,
right,
you will see the system maybe turn more into auto shock.
Right. Yeah. And also depending on what carbon and the whether the carbon in the rivers is more labile and less labile. And there's some literature suggesting the carbon to phosphorus ratio is over 1,000 because the semi-labile carbon in the system, and what's the residence time of the semi-labile carbon, and whether it stays and processed on the continental shelf is going to make a huge difference, I think.
Hello, okay. So
one of the things that we've been interested in is the relationship, I mentioned it in my talk, with priming. And as you start to make more phytoplankton, which enhances the sink idea, you can potentially kick in another feedback that makes it more of a source. Because as you start bringing in more water, you start bringing in more terrestrial material. So you have this sort of knee-jerk thing. You have the nutrients being picked up rapidly by phytoplankton, which translates into the sink. But as priming starts, as we find out now, priming now we just gathered some information looking at the leaching of, and with sea level effects, a lot of these peats that are in and around Florida, South Florida, as you leach this material out, most people would think that that would not be utilizable. But as you bring it in contact with phytoplankton exudates, that material is actually getting utilized. Some of it's 3,000, 4,000 years old. So as you start to increase sea level, you start to increase the net bleeding of terrestrial material, whether it's dissolved as well as erosional material going out. And that material, again, I think, as a result of the enhanced nutrients, and so there is that interface where you might get more CO2 being.
Yeah, no, yeah, that's true. But I was thinking about estuaries again, and I mean, estuaries are gradients per definition, and you have a lot of estuaries which are outgassing a ton of CO2 upstream, and which are actually a source when you arrive downstream. So there's a bit of a front somewhere where it goes from, and I mean, we made some simple simulations on sort of typical estuaries to have an idea of where this front might be moving in the coming decades. And I think keeping an eye on estuaries and where this limit between the riverine and marine estuary is evolving will be very interesting also in the future, because if the shelf are changing, maybe the most marine part of many, at least tidal estuaries, will change. And maybe other types of estuaries, like lagoon, might be still more protected and change less. I don't know, but I think that's something on which we should keep an eye.
Okay. We had a question in the back, and then we have Andreas and Debbie, and maybe others.
Hi, I'm David Ho from University of Hawaii. So I had a question about the choice of a gas transfer velocity. And I noticed that Iris chose Wanakov 92, which...
No, I used Jean.
Okay.
I used Jean Goodell,
Yeah.
2008, I think.
Okay. So that's a wind speed-based parameterization?
Right, we chose that because the wind speed was a better match for the wind speeds in our system.
Yeah. Okay. So...
And then we
you know,
compared it to your current, we had 3, and we compared them all. One was yours, one was, God, I've forgotten the other one.
Yeah. Okay. So my question is, you know, so in estuaries and maybe tidal wetlands, during different seasons, you might have different water levels, and also the differences in current velocities, which could affect the gas exchange. So when we're not using a parameterization that takes that into account, you know, how would that affect the fluxes that you determine?
We totally agree with you. But it's really difficult. You know, it's so variable on just a day-to-day basis. I did notice one thing when I was putting together my talk. We only go out when we're allowed to go out on boats, which means it's not very windy. I thought, oh, wow, that's biasing our results in a sense. But anyway, so I think that's I think that was beyond it requires, the models have to take into account, I think, currents and flows and seiches, all of that affects you know, what we're seeing, but it's just really hard to handle. At least, yeah. We didn't do it in what we've done so far. I wish we could have.
Did we have any other comments on that?
I guess I think this is an issue that is difficult and frustrates a lot of people who want to calculate gas fluxes from concentrations. And there's always a wind speed data set available, but there isn't always a tidal current data set available. So is there some workarounds? Is there some way to deal with that? And I mean, I've done the same thing that Iris has done. I've ignored, or I've tried to make a case that tidal currents are not important, but it's really difficult to do. Do we just have to have the tidal data there, or is there some way to estimate it from sea level, or some knowledge about the estuary?
Go to Debbie, and then Andreas. Wrong Debbie.
Okay, so I'll just be, oh, I really can't. So I wanted, Jesus, I am so sorry. So I wanted to follow up on Patty's comment about precipitation. So one thing that Barney Bulch has shown in the Gulf of Maine is that there's has been a big increase in delivery of terrestrial organic matter. And if you look at precipitation, it hasn't changed that much. It's gone up by like 10%. But how it's happening has changed dramatically, where you have many more of these events that are, you just get these torrential rains that are dumping a lot. It transfers a lot more organic material from land in than just a slow and steady rain. So has that been incorporated into any of this? Not the amount of precipitation, but how it's delivered?
Quality, the intensity.
The intensity, right.
So that's where freshwater discharge rates come in, right? So if it's more intense, you have greater freshwater discharge at a shorter flushing time. So we did try to take all that into account.
Isn't flushing time, isn't that annualized in terms of?
No, we did it day by day.
So one of my collaborators working on a land model came up with this theory as a memory effect of the soil. So what happens when you have dry year, you know, the precipitation is not really correlated with the amount of matter is being flushed to the outside, right? So if you have a dry year, even you have a little bit precipitation, nothing goes out. So it accumulates, and when you have a flushing year, you know, it's orders of a difference from the flushing rate. So that's called memory effect. I will refer you to Lee et al. 2019 Nature Communication. Yeah.
I just want to add to that. Let me just add to that. I think that another interesting aspect that you're bringing up is sort of this washout effect, right? So it takes time for the soils to build up that same amount of material, get it bound in the minerals and so on. So if you keep hitting that system frequently, that's going to be a very different type of signal of organic matter than after a dry period. It's not just the amount, it's also the quality of material. So that's another thing that complicates it. It's not just quantity with rainfall, just like you get washout with radionuclides in the atmosphere after periods of time. Same kind of thing with buildup of carbon.
Yep. Andreas Oschlies. I think a similar point applies to sediments as well, coastal sediments, which may change quite a bit according to extreme events, to management operations, and many things we may want to consider in Earth system models. And the question now is more to the model maybe, how should we couple land and ocean? Do we need, where's the boundary? Do we need a submodel in between, treating for coastal processes, which may be very nonlinear, and maybe an average residence time is in the long term not sufficient to account for all the processes like nitrous oxide emissions or sediment accumulation, carbon accumulation in sediments? What is your feeling for the next 5 to 10 years? What should be a good strategy now?
So I asked this question to John Dang. This is what he told me. He was telling me, to ultimately resolve this boundary problem, they were thinking, like Jeff Yall, they were thinking of having land everywhere on the globe and having the ocean on top of it. So instead of having a boundary in between, you just have the land on the bottom and the ocean on top. They were exchanging vertically, and then you have tidal fluxing, and then the boundary problem will be solved, and you have vegetation type on top. But he said that requires a lot of effort. Probably another 10 years. But I think it's really an idea.
Well, coastal ocean models, many of them do have wettable surfaces. The models that deal with flooding and inundation. But I want to bring up an area that Govan and I were talking about a little bit that I just wanted to make sure it got mentioned in this session that I think relates somewhat to your question and the question of boundaries as well. And that is, Govan actually posed this question formally to the group, so about how exactly do we define the coastal zone. But within that, there's an area that I'm very concerned about is that, and one thing that hasn't been mentioned very much are tidal wetlands. And they exchange a lot of material, as we heard in a number of the talks today. But we don't really know what the area of tidal wetlands is in the world. I mean, this is like a first order problem. And there's been some progress on this made recently with mangroves. There's a paper by Geary et al. that basically mapped, it's a very tedious and difficult thing to do, but mapped out all the mangroves in the world. So we have a pretty good estimate of mangroves, but for salt marshes and tidal fresh marshes, we just don't know. And if we're interested in scaling up and trying to understand what the kind of regional and global impact of this coastal interface is, we need to know the area. And I think we can say similar things about estuaries. They're a little bit, to me, they're a little bit harder to define. And so the question of defining what an estuary is, I think that's not quite clear. Even defining what the coastal ocean is, you have to make a choice. It sounds like Xiao made the choice for cutting it at 200 meters depth. But you can make other arguments for how to define the coastal ocean. So I just wanted to bring that point up and used your question as a means for that.
Yeah, we talked about that earlier, but I think we all have to be very transparent in what the boundaries of our budgets, field studies are or models are, so that there's no bits counted twice or left on the side. And so that's particularly clear on estuaries, for instance, but it's true everywhere. So I think it's sometimes, depending on what you are doing and what tools you have at your disposal, maybe you are not going to use the same definition as someone else, but as long as it's very clear where you stop so that people really can match together the different studies, it's really important. And it may sound obvious, but I think that has been the reason for so many mistakes in different budgets, like places, again, counted twice or totally left on the side. So, yeah.
Gulvan and
guys,
I were just.
Oh, sorry. No.
Gulvan and I were discussing that this morning. So for the York River estuary, do we say the boundary is the gauging station? Which is way up river and is very narrow and very turbid and very different than when the rivers come together and form what we call the estuary, which is broad, and a lot of light reaches the estuary. So the processes are totally different. So it's really hard to figure out, well, do we have to include everything all the way to the gauging station?
Was the gauging station at the head of tide?
Supposedly.
Yes. I mean, I do think the head of tide is a very defensible upstream boundary. But the downstream boundary, to me, seems hard to define.
You mean as far as compared to the coastal ocean?
No, like where you define the downstream boundary of an estuary. Maybe for the York, it's pretty clear, but sometimes it's varies with time. you know? So.
Hi, Dave Siegel, UC Santa Barbara. I have a question about the anthropogenic fossil fuel capability of coastal wetlands to sequester carbon. There's lots being talked about blue carbon, whatever in the heck that is. I just want to, just so, I'd love to hear your opinions on the matter.
Actually on my way to Scotland tonight for a blue carbon meeting and over the next few days. And one of the things that a lot of the people in these rocky intertidal areas are bringing up are sort of the importance of laminaria and some of these more rapidly growing species as blue carbon. They're not really blue carbon because the turnover of kelp is very, very different in terms of the release of CO2 back to the environment compared to a marsh, right? Because they have a hold fast, they're in oxidized sediments and so on. But to get back to what you're asking, is the only thing I've heard more recently with regard to that, Duarte and some of the others that have been pushing the blue carbon idea in terms of macroalgae, because that's, as they say, the elephant in the room, is to harvest and potentially use it in that way. So I'm going to a meeting. I have mixed feelings about it. I've kind of been the bad guy in saying that it's not the same as these other three seagrass, marsh, mangrove systems because the turnover and release. But then you have the idea of creating more mariculture kinds of systems that Norway's doing, and I think the consequences of that with what that may lead to in terms of other ecological aspects is not well known. That's all I can say about that. Since it's sort of timely with my own personal travel.
I'll say a little bit. First of all, every group defines blue carbon in marshes. It depends on how long. We spend days arguing when does it become blue carbon, and we settled on 100 years. It's been sitting there for 100 years, and that had to do with the turnover time in the atmosphere. But then last August, we had a lateral carbon export meeting here. David Ho was there. And no one's really done the mass balance. So if you look at how much CO2 is exchanged with the atmosphere, how much is exported as DIC or DOC, if you try to account for everything, there's not enough carbon there to bury it, export it, exchange it. And so we kept asking, where is the carbon coming from? And we never got a real answer to that. I don't think we know yet.
So, I mean, am I noting, like, is there a note of skepticism in your, about, Dave, about blue carbon and its sort of significance to the global carbon budget? Is that, I didn't...
As a sequestration tool.
Right. As a sequestration tool. I mean, I think it's definitely, it's sort of, I guess I put it like in the category of, what's the term I heard? Silver gunshot. Have you heard this term lately? Not a silver bullet, but silver gunshot. Like there are many solutions to climate change and carbon sequestration, and we need to deploy as many of them as we can. And there is a huge, tidal wetlands have a huge per unit area burial rate, and we certainly don't want to, we want to preserve them for lots of reasons, and I think carbon sequestration is one of them, and so it can help, but it's certainly not, and it's not, I don't think it's going to affect, for example, our projections of atmospheric CO2 in the future, that level. But I think locally it can be important. I think there's also, when you start putting a dollar value on carbon, it can add up to be quite a bit. And so to an individual state that has a lot of wetlands and seagrass and things like that, it may eventually be economically valuable in that narrow way.
Yeah, hi, Will Barrelson, USC. I might have missed it, but I haven't heard anyone mention the subterranean estuary, the groundwater, and its impact on some of these budgets that you're talking about, and it's changing over, anthropogenic timescales. Can you speak to that topic?
I've just talked to someone yesterday, and they told me he told me that in Gulf of Mexico, the groundwater and submarine discharges of nitrogen can contribute up to 40%. We're not accounting for it, but we don't know how much it's been changing, but there's an increasing realization of that.
Yeah, I mean, I certainly living in a state where there's a lot of karst, we hear about that all the time in Florida, and so to me, I always hear about it, but that's sort of the world I live in. I think, yeah, in this case, it's not up there, and so I think it tends to be very isolated to like these karst systems where people have to deal with that. I know there's been some work done off the Mississippi where it's been shown to be pretty significant as well. But I'm not a modeler, and I don't see it getting into the models as much. So I think Billy Moore, a whole bunch of other people sort of jumped on that for a while. It comes up sporadically, and then it just sort of went away in terms of the models. I agree.
Any other comments on that?
So there's a coastal hydrologist, hydrogeologist, Kevin Beefus, who's worked a lot on this. And I think he's going to have some good estimates for, I mean, first of all, discharge is poorly constrained itself, but he's developed a set of models, data-constrained models, to improve estimates of discharge along the east, I think along all of the U.S. coast, or maybe the East Coast and the Gulf Coast. And he's working on combining that at least with DOC measurements to get the DOC load. We made a back-of-the-envelope estimate for the East Coast, and it was something that we would have liked to have had better numbers for. Definitely couldn't dismiss it.
All right, well, we still have 3 minutes and 30 seconds. Any other burning questions? Must be something. There you go, Anand.
Thanks. So I wanted to ask a question of Tom Bianchi, but if anyone else wants to chime in, that would be great. Are there elemental cycles that we should be thinking about that we're not thinking about, like, say, sulfur?
I was just going to say sulfur. Yeah. No, I think now, particularly with some of the isotopic capabilities now that we're finding, and also just sulfur bridges and things like that that we've known about for long periods of time in biochemistry. There's been a lot of earlier work that was done with respect to kerogen and things like that over the years, but other than sort of the traditional marsh anaerobic cycle and its importance, it hasn't grown as much. The DSP, of course, stuff was moving in different areas across the air-water interface is not my area, but I am seeing more papers and talking to more people about some of these cycles now. And thiols and the importance of thiols and so on. It's even becoming involved. I mean, we're seeing some of that come into the CDOM components of amino acids and so on. So it's creeping in, I think, little by little, but I agree. I think sulfur is an important one that I can't elaborate on much better than that.
Any other panelists' comments on sulfur? Or other constituents that you think are important that we're not talking about? It's okay, you don't have to. Okay, well, we've got another minute. Are there any other questions? Yes, Jim.
Jim Bishop, UC Berkeley. I teach a course on aquatic chemistry and marine chemistry. And of course, the carbon system parameters are totally different. And it seems that there's special challenges in the estuarine environment. And I'm wondering if the panel members would talk about such things as ionic strength effects, the ion pairing effects that affect so much the ocean system, and how you go down an estuary, and what parameters do you need to know about the source waters in the estuary in order to successfully model the evolution of carbon chemistry in the estuarine system.
Okay, come on. That was a great question.
Go ahead.
So, estuary, I love estuaries because they're so complicated, difficult. So even diel variation, so just from morning to night, if you go and measure nitrogen, nitrate, or ammonium in the morning, it'll be really different than it is at night. And of course, there's stratification occurring, so it's really different in surface and bottom water. And same for many of the elements, not just nitrogen. So sulfate, sulfides. So it's really high, it's very labor intensive to collect enough data to take into account very temporal and spatial variation. So that's what
I mean, are you addressing maybe some of the uncertainties in the equilibrium constants, say at varying salinities? Is that your question sort of about that?
Yeah, you can't take the oceanographic.
Right, and just dilute them, right. Okay, so one thing I can say about that is that we're doing some calculations in Chesapeake Bay to calculate CO2 from pH and alkalinity. And we get very different answers depending on the set of equilibrium constants we choose in CO2 cis, particularly at very low salinities. So it suggests to me that there is a fair bit of uncertainty. It seems like the freshwater community's got a set of constants that they use, and the oceanographic community does. And then there's a lot of uncertainty and variability when you get to particularly brackish, tidal fresh and oligohaline waters.
So like magnesium ion is a big player in ion pairing, and
okay.
That's why the stability constants in the ocean for solubility of carbonate are like 2 orders of magnitude difference. Ionic strength effects take care of 1 order of magnitude. Magnesium does the other order of magnitude. Okay. So if you have river systems with low magnesium, then you're looking like freshwater constants, and you're diluting up to an ocean end member with linear change in magnesium. If you have a river with high magnesium, then the constants are going to be different.
Okay.
All right, well, I think we're out of time. First of all, I'd like to thank the audience for a lot of great questions, and I'd really like to thank our panelists for a lot of great answers.